Hi everyone, my name is Teja and welcome to this video series on the probability refresher for business analytics. In this video, we're going to look at the notion of random variables. Okay, and in particular, I'm going to use a notation which you might not have seen before, but it's very natural. And this is as follows. So a random variable x, I'm going to use a symbol capital letter to represent the random variable. It's actually a function. Okay. It's a function which goes from which takes every outcome or every element in the sample space um, and gives it a number. So from an outcome to a number. So every random variable essentially is a function from the sample space to a number. For example, um, okay. So since this is a function from the sample space to number, remember there was also another function that we came across, which was essentially the probability law itself, which was P, which you take an element from the sample space and pick a number, which would be um, between 0 and 1, right? So this is a number between 0 or 1, right? So probability law that we had seen a few videos ago was a function which gives for every outcome in the sample space a number, or not just of our outcomes, for a collection of outcomes, for example, for an event, right? So we wrote P of A and so on. So here a random variable is also a function. So there are two different functions, but one function is kind of more critical. Random variables, there could be many functions from the sample space to numbers, right? Many different functions. But this function is kind of critical. So let's now think of what a random variable kind of means. So for that, I'll also say that since fx is a function from the sample space to the number, in fact, what I'll do is, so this is a standard notation that you will see. I'll denote omega as a generic element or outcome in capital omega. So capital omega is the sample space, and omega is the, or I mean, this looks like W, but it's omega. It's a generic element in the sample space. Now, what I'm going to do is, so for this function, which is a random variable, capital X, okay, there's going to be there's going to be a probability law that corresponds to X. So if I define a random variable, so it's just a function, so I can define any function, right? Maybe a constant function, maybe an increasing function, maybe it takes, maybe my sample space has things like heads or tails or bananas, apples, and oranges. I can ascribe number to these outcomes. Maybe the outcome was a banana if I randomly picked a fruit from a ball. If it is a banana, maybe I'll assign a number 1. Maybe if it's apple, I'll assign a number 2, and so on. So I can define this function x, and once I define this function x, I can also get a probability law that corresponds to x. And what is this probability law? It's going to be related to this law that we have for the outcomes or for the events itself. So in particular, so there's going to be a probability law which is going to be related to this original function, probability, or the belief function that we had from before. So that's the notion of a random variable. I'm going to make this concrete in a minute, and in a broad setting, which is the setting of discrete random variables. Okay. So this is in contrast with what are called continuous. And I'm going to use notation RV to represent random variable. This, just to call random variables. So continuous random variables. Okay. Yeah. So discrete class of random variables and there's continuous class of random variables. Most of the concepts are essentially the same except for some minor differences. Discrete is kind of easy to understand because it just involves summations, like additions and multiplications, whereas continuous random variables will involve a bit of calculus. So let's ignore that for now and think about, we'll discuss discrete more. Okay, so in the discrete case, this probability law is called a probability mass function. I mean, a law is just a function, so it's just another name for function. It's just terminology. So we're going to call it the probability mass function. Okay, and an abbreviation of it is PMF. PMF. Okay. In capital letters or in lowercase. Okay, so this is the intuition. So let's see. So what is this law? So let me expand on this. So this law is going to say, as I said, x was a function which was, this is a shorthand to write what a function is. It's a mapping from omega to some numbers. Okay. So this probability law, I'm going to use this notation p of x taking the value little x. Okay, it just means that this function evaluates to little x. This is a way to say, if I can figure out what all values, let's say the function takes 3 values, maybe this some numbers is 3 values, 1, 2 and 3, then the probability law associated with the random variable will be just p of x is equal to 1, p of x is equal to 2 and p of x is equal to 3. Okay, so what does this mean? As I said, this probability law is nothing but something derived from the original probability law, which was something defined on the sample space, right? So this is nothing but a shorthand to say this. So probability of this collection of little omegas, which remember these I was using this to denote elements of the sample space. So omegas in the sample space such that x of omega, remember x is a function, so its input is going to be an element of the sample space, that's omega, such that x of omega is equal to 1. So this is what the shorthand notation means. It's literally a particular event. Remember, this is a subset of omega. This is just saying pick out all the outcomes such that this function, when acted on those outcomes, evaluates to 1. Okay, so this is an event. This is actually an event. We use the notation A to represent generic events, A, B, C, and so on. So this is an event. It's a subset of the sample space, and this event corresponds to the random variable taking a value 1. Okay, so a random variable is not it's not really random or shaky and so on. It's just a function. The probability law is what kind of gives that notion of uncertainty to this function. Okay, so this is the relation between events, sample spaces, and generic random variable. Okay, so let's actually look at. So first of all, one simple point that I want to observe is that, for example, in this case, since random variable is taking 3 values, the sum of the probability, this probability law of x taking the value little x, I'm going to use little x here, where little x is equal to 1, 2, and 3. This summation, this is a summation over little x, should be equal to 1, in the sense that the random variable can take value 1, 2, and 3. If I add these 3 numbers, then it should evaluate to 1. Okay, that's the, remember, even for our original probability belief on the outcomes, that was true. If you sum the probability values over all outcomes, it should sum to 1. Okay, I mean, our probability of omega is equal to 1. That was something that we saw before. Here, this should be true. And also that probability of x is equal to little x for any of these 3 values should also be greater than or equal to 0. And not just with these 3 values, I'm just telling in general, whatever the random variables values it takes, it should not take negative values and it should sum to 1. Okay. The same type of behavior that we were discussing with events and outcomes when we were actually discussing the axioms of probability. Right? So now let me give a very simple example just to double down on the concept. So let's say now we have a coin, right? We toss it and we can potentially observe a heads or a tails, right? So this is going to be my sample space, right? The only two outcomes. Maybe the coin is fair, so there's a probability that of getting heads is equal to 1/2, and so is the probability of tails. But these are not numbers, so we can assign a random variable x, which takes heads and gives me 1, and the random variable, which is a function, takes tails and gives me 0. Okay. Then we can talk about the same thing. Probability of x is equal to 1 is nothing but probability of heads is equal to 1/2. Okay. So this is just a way to, and this random variable is essentially called Bernoulli random variable. And even right here, I just want to briefly mention a connection to machine learning. So Bernoulli random variables are related to are essentially are very I guess very useful in machine learning. So let me just say that, for example, if you have binary classification, for example, if you're doing cats versus dogs, some classification problem, or maybe spam versus not spam, then you have two potential labels or two potential targets or classes that you can have for every input. For example, input feature vector. Then this outcome you would represent this label, you would represent it as these labels are not numbers, but you would correspond them to a random variable. For example, a variable y, which takes a value 1, for example, when it is cats, and maybe 0 when it's dogs, or maybe even -1 when it's dogs. Okay, so that random variable would be Bernoulli. Okay, that random variable will be Bernoulli. So let's continue with other examples of discrete random variables. Thank you for watching this video.